Okay, in this section, we're going to move on with synthetic division, using it to help us find the zeros of polynomial functions, or in other words, the solutions. We'll be calling them zeros when they give it to us in function form, and when they give us the polynomial in equation form, then we will move to use of the word roots, but they're really just all the solutions. When you do see these solutions in graph form, then they're going to appear as x-intercepts, and x-intercept is the same thing as a zero, same thing as a solution. So we'll be using our calculator to assist us somewhat, but we're going to begin by what's called using the rational zero theorem, where you are making a list of the possible solutions, but they're going to be in rational form, in other words, fraction form. So I'm showing you a function here in this theorem where a sub 0 is the constant and a sub n is the leading coefficient. And when you come up with this list of possible solutions, they're going to be in the form p over q. The p's will come from the factors of the constant, which they're calling a sub 0 here. And the q that you're seeing in the denominator when we make these fractions, that comes from right here. And again, they will be the factors of what's called the leading coefficient. They're calling it a sub n here. Okay, so we're going to work on doing that. I've written that definition for you again here. These are your p's. And the p's are nothing more than the constant, the term at the end that has no x on it, but there are various factors of that, and factors of the leading coefficient, which is what we refer to as the q values. Okay, in this very first problem, you're going to be making a list of possible rational zeros. Rational, again, just meaning that they're going to be in fraction form. You are going to be considering both the positive and negative form of these rational values that you're coming up with. So let's get at it. Okay, here's my list. I do want to consider both the positive and negative version of these values I'm coming up with, but I don't want to keep writing it over and over again, so I'm going to put the plus or minus out in the front. Remember, the p's come from your constant. Only way to factor this down is 2 times 1. So your p-value can either be a 1 or it can be a 2. Right here, the leading coefficient, that's where we get our q values. This can be broken down, factored down as 1 times 15, but also 3 times 5. So those q values that play the role of the denominator, they can be 1, 3, 5, or 15. Okay, so what I would do, just to, get a little rhythm going for yourself, is I would start with the smallest one and match it up with each one of these, going from smallest to biggest. So 1 over 1, 1 over 3, 1 over 5, 1 over 15. 1 over 1, 1 over 3, just so you make sure you pick up each one of them. 1 over 5, so I'm pairing this one as my numerator with each of these numbers as the denominator. And you can put them in order if you want. Make sure to take out any duplicates. I don't think they'll mark it wrong if you don't put them in order. But okay, next, I'm done with the 1. Now I'm going to pair up this 2 with each of these as the denominator. So you would have 2 over 1, 2 over 3, 2 over 5, and 2 over 15. And if you can reduce any of these, go ahead and do so. If there's any duplicates in here, go ahead and take those out. And you can, like I said, arrange them in order also. So this is what we call the list of possible rational zeros. And when we actually go to find the solutions for the problem, the numbers that we're going to try are going to come from this list. So you have to know how to generate the list. Now, as I had mentioned earlier, we are going to use our calculator to assist us somewhat, because sometimes you can be looking through this list for quite a long time. You're going to be trying these numbers using synthetic division, which is one of the main methods that we're using in this chapter? Well, it helps us, just as you've seen in previous section, to find out whether you have zeros. And so we're going to continue using it in that manner. So every time I do a problem, I'm going to start off by constructing this list of possibilities. And from this list, I'll have numbers that I'm going to actually try to figure out if they are the solutions or what we call the zeros. Okay, so in this problem, first thing I'm going to do is create my list. The factors of 30 are 3 times 10, 2 times 15, and also 1 times 30. So any of the numbers that you see here, 1, 2, 3, 10, 15, or 30, those can play the role of the p-values. And remember, we are setting up, let me just write it out here to remind you what the formula is. We're setting up all these rational values, considering both the positive and the negative form, where my p-values are the numerator and my q-values are the denominator. Okay, the q-values always come from the factors of the leading coefficient, which is a 1 in this case. And thank goodness that only factors as 1 times 1, so you only have one q-value because they're both the same. And that would be a 1. So that makes it really easy when the leading coefficient is a 1 because it doesn't break down. So here is my list. I'm considering both the positive and negative version of the following numbers. Again, I'm going to start with the smallest one here and pair it up with the only number that there is as a q value, which is 1. So it'll be 1 over 1. You can even reduce them as you go along. 1 over 1. It'll be 2 over 1. 3 over 1. That takes care of that number there, that number. 10 over 1. 15 over 1. And 30 over 1. So even though I'm going to continue with this problem in an effort to try and find the zeros, or in other words, the solutions of this function, things that zero it out, they are going to come from this list. And if you would like to put this function in your calculator, just the right-hand side of it, that can kind of help you to tell where to start in the list. But I'm going to start with 1. I'm not going to move over to the calculator, but I will put it in there to verify it. I'm going to try the number 1 to see if it works, just so I can run you through the process of figuring out when something works versus when it doesn't work. And every time that you actually do find something that is a solution, something that zeroes out the equation through the synthetic process, you're going to be bringing the polynomial down by 1 degree each time you find a 0. So right now I'm wondering if the number 1 is a 0, and I'm going to find that out right now through synthetic. Take these coefficients and write them horizontally. So 1, -4, -11, and +30. You always drop down that first value and begin multiplying. 1 times 1 is 1. You combine any two terms in a column, which is -3. 1 times -3 is -3. You end up with -14, and no, that does not zero out. In fact, you get a 16. If it's zeroed out in the last column as your remainder, we would call this a 0. We would say that this number is a solution, but it is not a solution. And that's because it did not zero out. Moving on. Now let's try -1. -1, take these coefficients and arrange them horizontally, just as I did here. And let's see if maybe -1 works. So bring down that 1. 1 times -1 is -1. Add these up, you get a -5. -1 times -5 is 5. Add these up and you get -6. This times this is 6. And again, that did not work. So this is also not a solution. It's not a 0. We use the word 0 when something zeroes out a polynomial. It's the proper usage of using the word solution is when it's actually an equation, but they just really do the same thing. Next biggest number, I've already tried both the positive and the negative version of 1, so I'm done trying that number. Now I'm going to try 2. So see all this work that I'm doing where I tried the 1 and the negative 1 and it didn't work. If you want to cut to the chase and just find a number that actually works, you could put this whole thing in your calculator, and if the graph runs right through a particular number as an x-intercept, then you know that that's one of the numbers that's going to make it zero out, or in other words, a number that's a solution. But I'm going to keep going just so you could see that, you know, sometimes you just go through this whole process. So this is a 1, a negative 4, some string of numbers, negative 11 and 30. Trying to see if 2 is a solution, so I drop down that 1 and multiply. I add these up and I get negative 2. 2 times negative 2 is negative 4, and then here I am getting my first answer. 2 times negative 15 is negative 30. You see that this zeroes out, which is the reason that it is called a 0. And that also means that when you plug in a 2 right here, it zeroes the whole thing out. So, you know, if this was an equation, if it was this whole thing set equal to 0, it would actually be a solution. So those phrases are used interchangeably. So find all the zeros. Let me keep track of them right here. This is the actual number that caused the zeroing out. So I'm going to keep track of my zeros here. 2 is one of them. And like I had mentioned previously when I started this problem, every time you find a number that zeroes it out, you do what's called decompressing the polynomial. So see this new string of numbers that you see right here? This is now a second degree expression, and that's because you started with third degree, but every time you zero it out, you bring it down a degree. So this expression that you're seeing right here is actually a second degree polynomial. So let's put the variables back on. We have 1x squared, we have minus 2x, and we have minus 15. And you create an equation out of this. This expression equal to 0. And once you get it to second degree, you don't have to try any more numbers in this list, because second degree, you already know a lot about that because you came into this class and you had already tried in the previous class even solving second degree equations by either factoring, quadratic formula. There are other methods besides that, but those are the two most common. You either factor it because it factors quite easily, or you go to the quadratic formula because you can't find integer factors. Now this one actually does factor. And very simply, you're breaking up that x squared to fill in the front position, and then you're looking for two numbers that multiply to give you 15 but add. Multiply to give you negative 15 but add to give you negative 2. And that would be negative 5 and 3. This times this is negative 15, but when you add these two things, you get negative 2. So that is factored properly, and then you use the zero factor property to create these little mini equations. It doesn't matter which one of these you write first, so I get one equation out of that. Oops, I wrote it wrong. Get one equation out of the x minus 5 and one equation out of the x plus 3. And then you solve them. This will give you the solution, or in other words, a 0. We're calling them zeros right now, x equal to 5. And this will give you another solution, x equal to 3. So that your zeros at the end of the problem are 2, 5, and negative 3. And those are the three solutions for that particular problem. 1 second. Okay, so moving on to the next problem, where we're going to start using our calculator just a little bit to help us get started in a more efficient way. Let's move to the next problem, where we have a third degree function. You're being asked to find the zeros, but let's actually make sure that you're practicing the skills that you're going to be expected to show when you take the test. So first, we're going to make the list of possible solutions, the list of possible zeros, as they can be called, by using the rational zero theorem. Okay, they come in this form, P over Q. They are rational numbers, and we're considering both the positive and negative version of all of these fractions. The actual p-values come from the constant. They are the factors of the constant. So for my p-values that I use on the top, it can either be 3 or 1. And then the leading coefficient here is where you get these q values. So the q's come from this leading coefficient. And that leading coefficient of 1 only factors as 1 times 1. So the only thing that q can possibly be is a 1. So we're going to do 1 over 1, and we're going to do 3 over 1. Okay, these are the only things that we have to consider. Now, if you want, now there's 4 different possibilities there. You could use positive 1 or negative 1. That's 2 of them. And you could use positive 3 or negative 3. That's 4 different things you could use. If you want to cut, right to the chase and find one that works right away instead of trying various values like I did in the previous problem until you find one, you can put it in your calculator. You're still going, even if you're going to grab one off the calculator though, you're going to show your work. So let me clear this out just so you can see how to use it. X cubed plus 7x squared plus 11x. And we had practiced in a previous section adjusting that window to make sure that we are seeing what we need to see on the graph. And we can see enough of this here. In fact, we can see that it goes through what looks like -1, -2, -3. Well, you know it has to be something from here. It has to either be a positive 1 or a negative 1 or a positive 3 or a negative 3. And I want you to notice that in this graph, it goes right through that value. It goes right through this value. And it appears that that's -3. Now, if you want to be sure that it goes right through -3, you could always go to the table. Because any point that's considered an x-intercept and therefore a possible solution, it should have a y-partner of 0. Any point that's on the x-axis has a y-coordinate of 0. So if you go to second table and you look at the -3, see how it has a y-partner? That means that it is a true x-intercept and therefore it is a true 0. So I already know that -3 is going to work. So I'm just going to use it as that very first value that I'm going to show synthetically divides into 1, 7, 11, -3. So that I can bring this thing down to second degree and finish the problem through either factoring or quadratic formula, whatever is required. Okay, the graph gave me a hint that that's going to work. I knew it had to be some number from in here. So bring this down. -3 times 1 is -3. Add these up. We already know this is going to zero out. Otherwise, it wouldn't have appeared as an x-intercept. 4 times -3 is -12. Add these up. You get -1. This times this is 3. And there you go, zeroing out. But every time you zero out, you bring the polynomial down by a degree. Down by 1 degree. So even though you started off with third degree, you now have a second degree expression. So this is 1x squared positive 4x. Remember, each term is 1 degree less than the one in front of it, and then -1. And you will create an equation out of this. This expression is equal to 0. This expression will either factor. It does not factor, because if this factored, you'd be able to find two numbers that multiply together to give you 1, which is only 1 times 1, but these numbers would add together to give you this, and they do not. Therefore, you must use quadratic formula, since this doesn't factor. quadratic formula to find the remaining two answers. And these answers that you find, they can be radicals, they can be complex numbers, they can be integers, so you have to be prepared to find them either way. If they're integers, you'll just be able to factor this. If they're not, you'll find them through quadratic formula. And those will be irrational answers, and sometimes they'll be imaginary and complex solutions. Okay, so here we go. Remember that this is called the A value because we need to know what A, B, and C is if we're going to use quadratic formula. This is B, and then C is that -1 that you're seeing. It's the number including the sign. Okay, so looking for the other two solutions. Right now, because this is zeroed out, we know that -3 is one of the zeros. So why don't we keep track of it over here? So it's -3, that's a 0. And really, to tell you the truth, if they're using the terminology called zeros, we really shouldn't even be putting it in a solution set. We're just listing the numbers. We're just listing the numbers that when plugged in here create a 0. When it's an equation, as it is in this next problem, solve the equation, then you can put the things that zero it out inside of a solution set. And they're called roots or solutions. So I guess I should take the bracket away from the answers that I gave in the last problem. But anyway, so we were trying to solve this right here and find the other zeros. So it's going to be opposite of B, quadratic formula, plus or minus. Underneath this radical, B squared again. So it starts with B, and then you're squaring B right here, minus 4 times A times C. All of that's underneath the radical, all on top of 2 times A, and then just continue. So it's -4 plus or minus, this is 16. -4 times -1 down the way would be +4. 16 plus 4 is 20 up underneath that radical with a 2 down here. Many of the problems that you're going to be facing will require you to be able to take a partial radical, and that's what square root of 20 is. There is no exact square root of that, but you can break it down into 4 times 5. The square root of 4 will come out as a 2, and this will now be -4 plus or minus. This 4 came out as a 2 because you're taking the square root as you release it. So that's gone. Get rid of it. Cross it out so you don't use it again. And the 5 stayed underneath, where the bottom is just a 2. Then I want you to consider these 3 coefficients that are on the outside of radical. The -4, the 2, and then the 2 that's in the denominator. If all 3 of those numbers are divisible by some common number, then you should reduce them. So this 2 divides into all of these. Don't mess with the 5. You've already done as much as you can do there. Okay, so then this ends up being -4 divided by 2, -2. Plus or minus. 2 divided by 2 is 1. Square root of 5. And of course the denominator is just a 1 now. So now you have 2 other zeros. So you know that your zeros for this particular problem are -3. -2 plus square root of 5, and then -2 minus square root of 5. And those are the 3 zeros. You'll just feed them into MyMathLab separated by commas. So just to be consistent, when you're finding the zeros, you really don't put them in a solution set. The problem will say solve. And when you're solving, you're finding a solution, so then you have the right to put it in a solution set. So you don't need the solution set. Just separate them by commas, and you can deliver them to MyMathLab in that way. Okay, by the time you get to this next example, where instead of giving it to you in function form, they gave it to you as an equation, now you're finding a solution set. So now it would be appropriate to use the solution set symbols, but the whole rest of the problem is the same. You're going to make a list. You're going to try the numbers from the list, but you can use your calculator to assist you with that and kind of cut out some of that work by just allowing your calculator to identify the value that you should use first. Okay, but let's practice composing the list of possible rational zeros. Okay, remember the p's come from the constant, so here's where we're getting the p's. And let's see, this can factor down as 8 times 3. It could also be 12 times 2. It could be 6 times 4. It could be 1 times 24. Leading coefficient here is just a 1, so your only factors there are 1 times 1. This provides the p-values, the factors from the constant. This provides the q values. Okay, so we're doing all possible p over q values. Kind of scoot this over. I'll put my plus or minus here, so that plus or minus applies to anything that I come up with here. So my p's, you can just go in order here. It's going to be 1 over 1, 2 over 1, 3 over 1, 4 over 1, let's see, what else, 6 over 1, and then let's see, we have an 8, a 12, and a 24, an 8, a 12, and a 24. So you see how that's like so many numbers. Where do you try? What if it's a number that happens all the way down here? You could potentially go through a lot of numbers using that synthetic division process. So again, you might want to use your calculator just to get you started. Also, the good thing about the calculator is when you feed it in to the calculator and you go and look at the graph, you can use some of your knowledge about multiplicity that we discussed when we were learning how to graph polynomial functions in a previous section. And that actually tells you something that I'm going to discuss with you about the solution that you're seeing on the graph. So let's see what a good number would be to try from here, because it's going to be an x-intercept. Just get right in here, clear out whatever is there, and go and feed in this polynomial. So it's going to be x raised up to the 4th degree minus 6x squared minus 8x plus 24. And if I graph that, this is the graph that I get. This is the actual shape for x to the 4th degree. But notice that where it hits, right here at positive 2, so 2 is the good number that you want to get this started with, rather than going through these numbers until you hit the one that, I mean, we would have hit it pretty quickly, but we still would have gone through positive 1 and negative 1, both of those failing before we ever got to this. So this kind of cuts to the chase here. But another thing, what I do really want to point out here is, notice that when this graph touches at positive 2, that it bounces right off of that number. Instead of the graph going through positive 2, it just touches positive 2. And if you remember when we were learning to graph, we would find the x-intercepts, and then we would talk about multiplicity. And if the multiplicity was even, we knew that this was going to be a touching point rather than a through point. Well, multiplicity also means something with respect to the solutions you're finding. It means that that solution repeats more than once. It repeats twice here when it has an even multiplicity. So because you're seeing the number 2, that means that the 2 would come up twice as a solution. So that means we're going to use it twice in the synthetic process, not just once. Because there's got to be more solutions. You have 4th degree, you need 4 answers. So at least we know the number 2 is very valuable. Not only is it an answer once, it's an answer twice. And that'll be any time you see a touching point at a particular number. Okay, and you might want to write that in your notes, that this x-intercept is a touching point on the graph. That means it has even multiplicity, and that means that you are going to use this particular number that you got off the graph twice as a solution. So let's use it the first time, stretching out these coefficients horizontally, so 1. Notice that the third degree term is missing, so we're going to put in a 0 for the third degree term. The 1 represents the fourth degree. This is third degree term. This is the second degree coefficient. This is the first degree coefficient, and this is the constant. Okay, drop down that first number to get the ball rolling and multiply. 2 times 1 is 2. Add these up, you get a 2. 2 times 2 is 4. Add these up, you get a negative 2. 2 times negative 2 is negative 4. Add these up, and you get a negative 12. 2 times negative 12 is negative 24. And we already knew that it was going to zero out because it's an x-intercept. An x-intercept is just what it looks like on the graph, but it means that it's a solution. Okay, so we now know that as far as the solutions go, now we have the right to put it in a solution set. We know that 2 is an answer, but 2 is an answer a second time. And whenever you are going to build on something that you already know is a 0, you're not going to go back to the original coefficients. You're going to continue your work on this new set of coefficients. So you were at fourth degree. That's when you started. You were at fourth degree. And every time you find a 0, you knock it down a degree. So this string of numbers that you're seeing right here would be a third degree expression if we were going to attach the x's to it, but we just want to keep rolling here. We know that the value 2 is a repeated solution, so put it right here all over again so we can use it a second time, only this time we're using it on this string of numbers, this third degree string of numbers. Put a line underneath it, leaving space right up underneath here. Drop down that first number and multiply. 2 times 1 is 2. Add these up, you get 4. 2 times 4 is 8. Add these up, you get 6. 2 times 6 is 12, which I knew this was going to zero out again because this is a solution more than once. So it made it zero out one time, and then it made it zero out again. So it's a solution twice. You don't actually have to list it twice, but we do know that if it's fourth degree that there's 4 answers, and by listing anything that repeats twice, you'll see that there's 4 answers. Okay, but the good thing is that by using that number twice, we now have this down to, we've now brought this down to second degree. This expression, this string of numbers, is a second degree expression, and you could put your variables right back on it and then let factoring or quadratic formula take it from here. Okay, so this is going to be your second degree term with a coefficient of 1. This will be your first degree term coefficient, and this will be your constant. Okay, now, does this factor? Well, if it does, the factors of this 6, which can only be 3 times 2 or 1 times 6, you should be able to, when you're going to factor this down, find 2 factors that multiplies to give you the constant, but adds to give you this middle coefficient, and that just doesn't work here. 3 plus 2 is 5. 1 plus 6 is 7. So no pair that you have over here is going to add to give you that middle coefficient. Therefore, it does not factor. And you must continue the problem because you need to find 2 more solutions. You only have 2 so far, and there are 4. Maybe you can write that. There's 4 solutions because the number of solutions are dictated by whatever the highest degree is. Again, these answers can be integers. They can be complex numbers. They can be irrational numbers that don't have complex numbers in them. So let's continue. We've figured out that this won't factor, so therefore to solve this second degree, we're going to solve by quadratic formula. You can either use the factoring or the quadratic formula to take it from second degree to the last two answers. So that formula goes like this. X is equal to opposite of the b value. That's your b value. A is 1 here, b is 4, and this is c is equal to 6. So it's opposite of the b value plus or minus b value again, but squared, minus 4 times a times c. All over 2 times a, and that a value is just 1. So whittling this down a little bit, this is going to be 16 minus 24. 4 times 6 is 24. So when you continue with this, it's going to be the negative 4 out front, plus or minus, and then 16 minus 24 is negative 8. So we do have an imaginary number here. 2 right here. Again, this is not something that there's a perfect square for. Numbers like 16, 25, 36, those are all things that have perfect squares. This only has a partial square root. Break it down so that one of the factors you can take the square root of. Okay, so what you're doing here, just so you recognize what's happening here, you have negative 4 out front, plus or minus. Underneath the radical, you have negative 8, which is negative 4 times 2 over 2. The square root of this is 2i. Anytime you're taking a square root of a negative number, that's going to come out as an I. Square root of 4 is 2, but because it has a negative, 2i. So now you have negative 4 plus or minus 2i. You're done dealing with that. Cross it out so you don't use it again. That 2 stays underneath. And you have a 2 right here. If each of these coefficients, the things that are on the outside of the radical, are all divisible by the same number, then you can reduce it. Everything divides by 2. So it's going to be, when you reduce this, negative 4 divided by negative 2, negative 2. 2i divided by 2 is 1i. Square root of 2 hanging off the back, and you have a 1 as a denominator. So these are your other two solutions. And you can write them separately, of course. This is me writing it compactly just because I don't have much room here. But in my math lab, you'll probably list them separately. 2 plus I times square root of 2. And you can put the I in front, the I in back. Just don't put the I underneath the radical because that means something else. And the other answer is 2 minus I times square root of 2. And there you go. 4 different solutions. Okay, moving to yet another problem. That is 4th degree. Again, we're going to have to knock this down twice. The whole goal here is to get it to 2nd degree so that you can finish it by either factoring or quadratic formula. And how you get started with the problem is you're going to make a list, and in that list will be some numbers that will help you zero it out. To know which numbers to use from the list, yes, of course you could go through every one until you find the ones that work, but that would be pretty time consuming. So we're going to make the list, but then we're going to use our calculator to give us a hint of what we should try first. The list of possible zeros right here. We are doing them in fraction form because we're using the rational zero theorem. So here we go. Remember that the p's come from right here. That 6 factors as 3 times 2. Don't worry about the negative because you're already hitting up that positive and negative, both positive and negative right here. It can also factor as 6 times 1, and then we have a nice leading coefficient of 1, therefore your Q values can only be 1. So we could have 1 over 1, both positive and negative version of it. We could have 2 over 1. We could have 3 over 1. And we could have 6 over 1. So although there looks like there's only 4 items here to try, there's actually 8. Because you can try plus or minus 1, plus or minus 2, plus or minus 3, plus or minus 6. But just to avoid trying too many of them before we hit our very first one that works, we can use our calculator. And you might want to snatch a couple of things that work. So, because remember, for each thing, for each number that zeroes it out, you're going to be knocking it down a degree, and we need to knock it down twice. So we'll grab 2 values that work, but we'll still show the synthetic division. You need to show that you understand the concepts being taught in this work and that you're just using your calculator for mild assistance, not to do the whole problem. So please do not put this in your calculator and say, I saw all 4 answers in the calculator, so that's why I didn't need any work. No, you do need the work. Just use it a little bit, not to do the whole problem. So let's see, clearing this out, and we're going to put x raised up to the 4th, then we have minus 5x up to the 3rd power, plus 5x squared, plus 5x minus 6. Graph that, and we can see a bunch of answers here. We can see -1 works, +1, so why don't we just go and grab those 2 things and use those to knock this thing down to 2nd degree. And of course these make sense because both +1 and -1 are in this list of possibilities as things that could possibly be solutions. Nothing but these numbers can be your possible rational zeros. So we saw that the graph went right through -1, so let's use that. Our coefficients are 1 for the 4th degree term, -5 for the 3rd degree term, 5 for the 2nd degree term, 5 for the 1st degree term, and -6 for the constant. Drop that first number down, multiply. Add these up, you get -6. -1 times -6 is +6. Add these up, you get 11. And then -1 times 11 is -11. Add these up and you get -6. -1 times -6 is +6. You add these up. We already knew that this was going to zero out, and that's because this number is an x-intercept on the graph, which really means that it's also a zero of the polynomial, or in other words, a solution of the equation. So we know that -1 works, and I do have the right to use these, the solution set, because I've been asked to solve. So you have a solution set. We also saw that this graph went through +1, but you don't start all over again. You work on this decompressed string of numbers. This string of numbers where you are now at 3rd degree, because you want to keep going down. And if you're going to keep going back to the original string, you're just going to keep being back at 3rd degree, and therefore factoring and quadratic formula won't work to get you to the final 2 answers. Okay, so now we're going to use, +1. We already used -1. So now we also saw that the graph went through +1, just as we saw it went through -1. We're using this new string of numbers. Let me move this up just a little bit. Okay, so you're dropping that first number down. 1 times 1 is 1. We're going to add these up, get -5. 1 times -5 is -5. Add these up, you get 6. 1 times 6 is 6. Add these up, and here we go, zeroing out again. Again, we knew that this was going to happen, another zeroing out, because this was also an x-intercept. But in getting this thing to zero out twice, we've brought this down with respect to degree 2 times. We were at 3rd degree by the time we zeroed out the first time. Now we're at 2nd degree by the time that we zero out a second time. And you can put the variables back on there. This is 1x squared. This is negative 5x. And this is positive 6 with no variable. And it is equal to 0. Okay, now that factors. So don't bother going into quadratic formula if it factors, because it's easier and quicker to factor. Break up the first term, x and x. Break this up into two factors such that they multiply to be 6, but they add to be 5. That's going to be 3 and 2, both with a negative. Negative 2 times negative 3 is 6, but negative 2 plus negative 3 is that negative 5. Okay, creating little baby equations out of each of these factors. Using this factor set equal to 0, we'll get one solution. Setting the x minus 3 equal to 0, we'll get another solution. This gives us 2, and this gives us 3. Okay, so we found out 1 was an answer. We found that out through, negative 1 was an answer through synthetic. We found out that positive 1 was an answer through synthetic. By that point, we were at second degree right here, and we finished it with factoring. And we found out that our third answer was 2, and our fourth answer was 3. And those are the 4 solutions, verifying that's fourth degree. 4 answers, they just all happen to be integers this time. So I wrote this theorem down here for you, that if a polynomial equation is of degree n, this problem that I just did was fourth degree, then counting multiple roots, anything that repeats twice, if you want to see that you actually have 4 answers, you should list that answer twice. Not that you have to when you give your final answer in my math lab, but just to verify. And that sometimes your roots can be imaginary numbers, they can be complex numbers, and specifically what I want you to take away from this property that I'm sharing with you right now is that your answers that are complex numbers like that, they always occur in conjugate pairs. That's going to be important for some of the problems that we're going to do next, where you're going to be taking this process and going backwards. And you can see that in the previous problems, that whenever you do have an answer of this type, where you have a complex pair, complex numbers, the conjugate is always a solution. See, we can look on the previous page in the problem that we just did a minute ago. Look what the last 2 answers look like. This is a complex number, negative 2 plus, where it's part real, part imaginary, negative 2 plus I times square root of 2, and negative 2 minus I. Whenever the I term has the opposite sign, it has the opposite sign, those are called conjugates. So they will always come in that form when you do have a complex solution. These just happen to be all integers. Okay, now moving in the reverse order, where instead of being given the polynomial and you look for the solutions, now we're going to give you the solutions and you look for you come up with the polynomial. So right now, by being told that n is equal to 3, this refers to the degree of the problem. So when you do get done with this problem, you should have x to the 3rd degree in there. Okay, they're giving you 2 of the solutions. You know that if you're of degree 3, that you should have 3 answers. But remember, we just read a property about when there are imaginary numbers and complex numbers, they occur in conjugate pairs. Any kind of imaginary numbers or complex solutions. So if positive 2i is a solution, a 0, then so is negative 2i. It's conjugate. This is the conjugate of that. You just switch the sign on the I term and you have the conjugate. So negative 2i is also a 0, even though they don't give it to you, but by that property that we just read on the previous page, it is also a 0. Since those type of solutions always occur in conjugate pairs. Okay, and now we begin with the problem. These problems are quite long. This is the milder version of the problem that's on the next page. That one's even a little bit harder with respect to the algebra, but all of the steps are pretty much the same. Okay, so we're going to start like this. According to this linear factorization theorem, when you are trying to come up with a polynomial function, you'll have your leading coefficient out here, and then each of the things that are called solutions can be written in factored form. And what they look like in factored form is they always have the opposite sign of what they have when you're already seeing the finished solution. See, these are finished solutions. And when they're in factored form like this, they have the opposite sign. So that the way that you're going to get that to happen is you're going to go like this. To make these have the opposite sign, you're just saying, okay, here's my leading coefficient. I'll just call it A. I know they called it A sub n, but we don't need subscripts here. And for each of my solutions, I'm going to go x minus the actual solution. One of them is 3. That'll make the sign switch. They should have different signs here than they do when they are in their final form. Another solution is positive 2i, so I'll go x minus 2i. And then another solution was negative 2i, so I'll go x minus negative 2i. Okay, then I'm going to clean this up a little bit. Just clean up the double negatives that you see in that last parenthesis. And I'm going to begin multiplying this out. I'm trying to get a function here of third degree. Easiest thing in any of these problems where you have complex conjugates, where you have conjugates, multiply the conjugates out first, because there is a shortcut for foiling conjugates. That's why you want to tackle that first. And the shortcut is square minus square. Okay, whenever you have two conjugates, you can get all the foiling done like this, rather than going this times this, this times this, this times this. That's a lot of steps. You're into 5, 6 steps there. Here you can just either be looking here or here. You don't need to look at both of them. And you're going to square the front term, square the back term, and then put a minus in between them. And that'll get it all foiled out, but save you about 3 steps. Okay, so here we go. Square this front term, you get x squared. Square this back term, you have to square the 2 as well as the I, so that would be 4i squared. And throw a negative in between them. Okay, the square minus square is how it's a shortcut for foiling conjugate binomials. These are binomials and they're conjugates. Okay, now let's clean this up a little bit. I squared is defined as -1. Bring down that -4 multiplier. This times this is +4. So all of this foiled out is x squared plus 4. Drop down that x minus 3, the leading coefficient, and now let's work on getting this foiled out. Now here there is no shortcut, so you're going to actually have to use traditional foiling. First times first, outer times outer, inner times inner, last times last. You're going to have to go through all those steps. So this is going to be x cubed, x times x squared is x cubed, x times 4 is 4x, -3 times x squared is -3x squared, and then -3 times 4 is -12. Don't forget to bring that leading coefficient down. Okay, so now we have a cubed term, a squared term, a linear term, and a constant, and we'll put those in order later on when we give our final answer. But right now, we don't know what the leading coefficient is. And so now it's time to bring in this additional information. We know what degree it has to be, and we do have a third degree term. We've already used the zeros, and now we bring this into the game. This says f of x, letting x be 2, is equal to 8. That's your y value. So let's jot that down right here. When x is 2, y is 8. All of this stands for y. And this is saying when x is 2, your y value is 8. So let this be 8, this entire function name, which stands for y. You don't know what a is yet, but when y is 8, x is 2. So we're going to come in here inside the parenthesis and we're going to do 2 cubed plus 4 times 2 minus 3 times 2 squared minus 12. And you can use your calculator to help you get that simplified, but it's 8 plus 8. Then this is 4 times 3, negative 12, minus 12, times a. Okay, so this is going to be 16 minus 24. That's what's in here. That ends up being negative 8. Times a, and you have an 8 over here, and you're solving for that. So you're solving for a, so divide this negative 8 right off of the a, likewise over here, and you end up with a is equal to negative 1. So now you can go and give your complete answer, come right back up here. The only thing that we did not know about this function after we got this all multiplied out, now let's see, at what point did we actually have a function without any i's in it or anything? I believe that was right here, before we started plugging the 2's in. So we now know that our final function is, the a value we just found out down here is negative 1. So our function is going to be negative 1, and then in the terms of the polynomial are x cubed. We have a negative 3x squared term. We have a positive 4x, and we have a negative 12. And if you drag that negative 1 in there, then you have negative x cubed, positive 3x squared, minus 4x, and negative times negative 12 will be positive 12. And that is your finished function. And yes, those are a lot of steps. There's no way to get around it, but the good news is that this was the easier of the two problems having to do with this, because you only had solutions that were a single term. Sometimes these imaginary numbers can be hooked to a real number, in other words, a complex number, and that makes the algebra slightly harder, but we don't want to leave out the hardest problem, so let's go ahead and do one of those. You will see one in my math lab. Okay, so again, reversing the process again in this problem and coming up with our own function rather than being given the function. It's going to be third degree again. Okay, the solutions are negative 4. This is a second solution, 6 plus 4i, but whenever you have a complex solution, the conjugate of that is also a solution. Okay, complex solutions always come in conjugate pairs, so it says one of the properties that I gave you on a previous page. Conjugate of this, you just switch the sign on the imaginary number. So 6 minus 4i is also a solution. So those are your three solutions, because it is third degree. So it should have 3 solutions. And even though they only listed 2 of them, you know by the property that I taught you that its conjugate counterpart is also a solution. So negative 4, 6 plus 4i, and 6 minus 4i. We'll use this at the end of the problem to find a. Okay, so here we go. F of x is equal to some leading coefficient, and then let's put each of the factors now by the factorization theorem. So it's x minus the first 0, which was a negative 4, and then it's x minus the next 0. Oops, making a mess here. Okay, so the next 0 was 6 plus 4i. So that was another 0. And then another 0 was x minus 6 minus 4i. Okay, so now dragging this negative through, it's going to be negative 6 minus 4i. Negative 6 plus 4i. And still trying to look at this as conjugates, and I'll clean up this double negative and write it as an x plus 4. I'm still looking at these as conjugates. See how I had the parentheses around the back two terms? Well, now I'm going to slide them up and let them be around the front two terms, just so you can see that you're still dealing with conjugates. We're still looking at this as though it's a binomial. First term, second term. First term, second term. Notice that the first term is the same for both of these, and the back term is the same for both of these. Only one's a negative and the other one's positive. So these are conjugates. And to avoid a lot of aggravation and work, we're going to use the shortcut for getting all of this multiplied by all of this. We need to get that all FOILed out, and we can just use this shortcut right here. Square the first term, square the second term. Again, this is considered the first term of each of these expressions, and the 4i is considered the back term. So when it says square the first term, you will be squaring that binomial. Let's just write it like this for right now. And when it says square the back term, you're just squaring that 4i. Don't forget to square the 4 as well as the I. So that'll be 16i squared. This minus goes in between the two squares. So I just got all of this FOILed out. I'm not done with it, but it's the easiest way that you could tackle something like that. Okay, so let's keep working on this, and then we'll pull down these other items. All right, there also happens to be a shortcut for FOILing this out. Whenever you're taking a binomial and squaring it, you can use square, double, square. And I'm going to keep going over these shortcuts with you because they are pretty handy when you're already into a problem that has a massive number of steps and you're not trying to add another 10 steps to it just because you don't know the shortcut. So for binomial, where you have two terms squared, it's square, double, square. I've been going over the conjugate FOILing shortcut. This is a FOILing shortcut for squaring. You square the first term. When you double, you first multiply these two things. It would be negative 6x. Negative 6 times x is negative 6x, but then double it. When you double 6x, you get 12x. And then square again, just square the back term. Plus 36. Okay, so that's all of that squared. And then minus 16i squared is really this. It's minus 16. I squared is negative 1. Negative 16 times negative 1, positive 16. That's what that negative 16i squared is. It's negative 16. So inside this bracket, you can use parentheses or brackets, either one. I get tired of using parentheses and I like to switch over when there's too many parentheses. So inside here you have x squared, you have minus 12x, and you have a 52 as far as your constant. 36 plus 16 is 52. Now drag that x plus 4 in there because you're still trying to create this polynomial. And we still have some steps to go. Okay, so look what I got in here. I had, from up here, I had two conjugates. Oops. Okay, front terms matched, back terms matched. That makes them conjugates as long as the signs are different. I did the shortcut for conjugates, which is square minus square. So I squared this and I squared that. When I went to square this, there was also a shortcut available for that. Square, double, square. That got me x squared minus 12x plus 36. And this negative 16i squared turned out to be positive 16. I then combined this and this to get a 52. Now I'm going on with creation of my polynomial. I need to multiply all of this, x plus 4, times all of this. So there is no shortcut. You're going to have to just do straight on traditional FOILing. It is extended FOILing because you're doing 2 terms times 3 terms. So it's going to be x times x squared, x times negative 12x, and x times 52. That'll be 3 products. Then it's 4 times x squared, 4 times negative 12x, and 4 times 52. So instead of the typical 4 products, you're going to get 6. So x times x, just follow the arrows, x cubed. X times negative 12, negative 12x squared, and then x times 52, 52x. Upside down arrows, 4 times x squared, 4 times negative 12x is 48x, and then 4 times 52 is going to be 208. All of this by being multiplied by the leading coefficient, which again we still don't know. Let's clean this up a bit before we go plugging anything in for x. So we have one cubed term. We have negative 12 plus 4, that's negative 8x squared. As far as our linear terms, we have 52 minus 48, that's 4x. And then our constant is 208. Okay, so finally after you get everything multiplied out on the right hand side, that's when it's time to bring in this last bit of information that the function with 1 plugged in for x gives you 205 as your y value. Let's transfer that down here. F of 1 is equal to 205. Once again, that means when you use this x value that you get that y value. And we're going to use that in order to find a. This is your y value right here. It says when y is 205. X is 1. So everywhere that you see an x, you're going to put a 1 in there. So it's x cubed. It's negative 8x squared. It's 4 times x. And let me see, what did I just plug in here? I'm supposed to be plugging in a positive 1. So it's negative 8 times 1 squared, and 4 times 1 right here, and then plus 208. Okay, and you can get your calculator to assist you if you'd like. So it's 1 minus 8 plus 4 plus 208 times a is equal to 205. And then you can put these in your calculator. 1 minus 8 plus 4 plus 208. $205. Good. Perfect. So everything added up in here was 205. And there's a 205 here. So therefore, if you're looking for a, the leading coefficient, it has to be 1. Because you'd be solving for a here. Turns out that a is 1. So now when you go to give your final answer, it's f of x is equal to, and let's go back to the step where we had gotten the entire function, but we just didn't know what the a value was, and that is right at this point. Right there. So going back to that, but now knowing that the a value is 1, if you're going to put a 1 in there and multiply 1, and I'll just go ahead and write it even though I know I don't really need to see this, but I like to be nice and thorough. Okay, so after all that work, of what we did right here, we found out that a was 1, and therefore your final answer, usually you, whatever it is, you just distribute it, but since it's a 1, of course, it's not going to change anything inside the parentheses. It'll just be x cubed minus x squared minus 8x squared plus 4x plus 208. And that is your final function given all the parameters they gave you at the beginning of the problem. Okay, that completes section 3.4. And I'll see you again soon for section 3.5.